In the next section, we'll look at how to construct these string matching automata that work so well for finding the occurrences of a pattern in the text. And again, for those who've had some automata theory, have been tortured with a bit of that in some previous lecture, maybe you know about NFAs. If DFA stands for deterministic finite automaton, then NFA might stand for non-deterministic finite automaton, and it does. These are all kinds of automata that are not deterministic. It's kind of it doesn't really say what they are. It just means that they can leave some parts up to ambiguity. And in a way, the easy part to build this string matching automaton was just writing down the pattern on edges to the right and leaving the automaton as it is. If you additionally allow the automaton to stay in state 0 for all letters, you've actually built a valid non-deterministic automaton for this language sigma star p sigma star. It's kind of not so useful algorithmically, but it will help in an indirect way. I just want to point out for those who haven't used these automaton, the way they're reading an input now means when I start in state 0, even if I read an A, I don't have to go to state 1. I can also decide, this time I'd actually rather stay in state 0. And then reaching the final state means there's some way to choose among these options that gets you there. Or another way to put the same is, instead of being in a single state, it's kind of a parallel or all possibility universe quantum world. You're always in all possible states where you could have been if you made the appropriate choice. So if I'm initially in state 0, deterministically, and I read a letter A, I branch out into being in state 1 following this edge and in state 0 simultaneously. Okay? And from then on, you always have to go, where could you end up from all the states where you currently are? There's no real quantum involved in this. It's all just saying you're in a set of states. And so you can read the text we had before. It's the same example if you want to go back at home. We're initially in state 0. After reading A, we're in states 0 and 1. After reading another A, if we're in state 0, we go to state 1. OK, we already had that. And we can also stay in state 0. If we're in state 1 and we read an A, the automaton doesn't tell us where to go. That means that branch, that parallel universe just collapses. It dies out because there's a dead end. OK? So if you're in states 0 or 1 and you read an A, you're afterwards still in states 0 and 1. If you're in these two states and read a B, it's a little more interesting. From state 0, B means you can stay in state 0. So you get that state 0. But you could have also been in state 1 and then read a B that brings you to 2. So afterwards, you're in states 0 and 2. And then things get more wild. If you read another A from here, you can either be again in state 0 or in state 1 if you were in 0, or from 2 go to 3. So you can be in any of 0, 1, or 3. And so on and so forth. Now, you found an occurrence whenever 7 is one of the possible states where you're currently in. That's the way to read this. And that's actually not a terrible way to think about string matching. It's just not such an efficient way. And we already know a somewhat OK way, the brute force method. And in a way, this one is essentially not much better. The point is that we have to maintain this set of states. And the worst case, it's the whole set. And then every transition needs to go through all the states you could be in. So you end up with essentially this n times m worst case. Very similar to the brute force method. OK, so was this all not useful? Another piece of theory. For any non-deterministic finite automaton, there's an algorithm to construct an equivalent deterministic finite automaton. Now we're getting closer. That algorithm is called the power set construction. And it basically works by using, instead of the states we have, all possible sets of states as your states. So every state is a set of states from the previous automaton. And the transitions essentially work like in our example. Okay. And then there's even an algorithm to find a smallest possible DFA. So in a way, again, both of these problems are kind of solved. But from a practical point of view, the concern is that the power set is an exponential blowup. Even if you can minimize the states away afterwards, that's really not helpful. We don't want to have an exponential blowup. And this is where we get to these three names that will pop up later again. Somewhat independently, Knuth, Morris, and Pratt came up with a few related ideas that help to avoid this exponential blowup. And the first of these ideas is that we don't have to go black box from NFA to DFA and then minimize it. We can build the automaton instead step by step. And if you remember our example from before, this was the string matching automaton I've shown you for our example pattern. How many states did it have? Well, just m, or m plus 1. Because the states had this specific meaning. Let's hope that this is general, and we always need just m plus 1 states, and not 2 to the m or something crazy like that. And they made the following observation, which I guess is, okay, sorry, I'll go back to the example one more time. Maybe instead, let me just copy this. Then we have it a bit more nicely drawn. So let's suppose we're trying to find the transition from state 3 when reading a letter A. So we're trying to find this edge. But suppose we don't know where it goes yet. Now, the idea of Knuth, Morris, and Pratt is we add the next letter of the pattern one step at a time. So we assume inductively we've already built this part of the automaton. Everything that involves the first 3 states is known to us. Now, I have to draw more pictures. Remember what it meant to be in this state 3. It meant there's our text, and then it meant that there were the first 3 characters of the pattern that we could read up until this point, and no longer a prefix of the pattern was possible to read up to this point. And now the next letter that comes is an A, which is not a B, which would be the next character in the pattern. And so we somehow have to shift the pattern a little bit further. And that is spelled out here, but let me show it in the example first. So the actual letters that go here are A, B, A. And we know they match the text. So the text ends with these 3 letters, A, B, A. And then comes another A. Now, we know the automaton should now go to the state that tells us what's the longest prefix of the pattern we've seen if we read the A. And if we just figure this out manually, we could try to shift it by 1. But we see that's a mismatch with what we've seen from the text. So that doesn't match at all. If we shift it by 2, that's a bit better. But it would still mismatch with this A here. I should probably draw it like this. So the best we can do is shift it all the way along so that only the A is aligned with the next letter that we're reading. So the state we should go is state 1. And of course, that's also what the automaton does. But how can the algorithm find this out using this green automaton without all this case by case and thinking through? Well, it can do it by pretending we're reading the text one more time. So we're reading what we know about the text, A, B, A, A, except that we leave out the first letter. Why do we do that? Because we already know that's not matching. So we know the longest prefix that we can still find is definitely not 4. It's at most 3. So we just start reading with 3. So we take BAA and look where the automaton A2 ends up after reading BAA. If we start in 0, we read a B, still in 0. We read a 1 to an A to go to 1, and we read another A, we're still in 1. So that's our result. So here's spelled out in words again in general what this looks like. The new transition should still be, according to the same invariant, the longest prefix that matches this. And that has to be a suffix of the pattern when I chop off the first character. So note here is starts at 1, here it starts at 0. And that's the state of the automaton that I've previously built when I start reading the text with the first character dropped. If you try to do it exactly like that, it doesn't look like it's very efficient. But it turns out we can avoid that. But that's still a useful way to build the automaton. Let's do one more example where we try to find delta of 5 and B. So when we're trying to find the transitions for state 5, we know that C brings us to state 6. That's the match edge. And for the other two transitions, for example, B, we have to look at what we already have. And the previous automaton we have is this part, A up to including 4. Being in state 5 means we've seen the first 5 letters of the pattern. And the first 5 letters of the pattern are A, B, A, B, A. And now we're reading a C, sorry, a B, and we drop the first character. So we look in the blue automaton, where do we end up when we read BA, BA, B? Start at 0, B, A, B, A, B. State 4. And that's where we're supposed to end up. Okay. So manually, it's not a terrible way to build it for a small pattern. If the pattern gets very, very long, and you do this exactly following the steps like this, you will naturally lead to the algorithm that I'll show you next, which does this a little faster, because you keep doing the same things. And to kind of give you a chance to see that in action, let's do the other transition for A. So again, we read in the blue automaton, but this time BA, BA, A. All right? We start in the beginning. We read B, A, B, A. And then instead of a B, we have an A, which brings us back to state 1. Now, you may have noticed that the paths for the green and the blue parts, they all start with reading BA, BA. There's no need to simulate the automaton each time from scratch. Instead, I could have gone BA, BA. So I remember after reading BA, BA, I'm in state 3. And then I can go one edge for B and another edge for A. All right? I'm always reading with the automaton the same prefix, and then one letter at the end changes. That's only the last state that is different. All right. That's the second insight of the three names, the people behind the names, Knuth, Morris, and Pratt. The simulations of this smaller automaton only differ in the last step. So why don't we remember where we've been? And you can push this one bit further with this algorithm by noticing if you go from one automaton building, okay, back to my example last time. If you go from now constructing the transitions from state 5 to constructing those for state 6, this blue automaton gets a little bigger. I add one more state. But I can also track that the prefix I read of the pattern also just gets one longer. So when I was in state 3 before reading the last symbol, because I read BA, BA in this blue automaton, once I go to the one bigger one, I add the BA, BAC. So I go from state 3 to state 0, and that's the state where I start reading from. So it should say from state 6, whenever I read something that's not an A, that's the same as reading that from state 0. And that's indeed true because B and C stay in state 0. From state 6, B and C go to state 0. That means constructing the automaton here in the code as computing this transition function in an array is very, very short and simple. I'll show you on the example. First of all, we initialize the first column to all zeros. But then we override the match edge. So state 0 and the first character of the pattern A should instead go to state 1. That corresponds to the one matching edge that goes to the right. Now I maintain also this state X where I was when I read the one pattern, the pattern without the first character. And initially I'm in state 0. Now I go through all the columns of the table. And the first step is I copy the column from column X to the next column where I'm filling things in now. So my J is 1. I'm looking at this column. First step, just copy the previous column because that's where X is. But we overwrite the match edge. That's the only change we do. So we're in this case, the match edge should be for B. So here we put a 2 to go to the next stage, the next state, instead of staying where we are. And the last bit is update X. And that means we're in the column of X, and we read the next character of the pattern, which is B. So we're in this, we read a B, we stay in 0. So 0 is still correct. Let me do it one more time. We copy the column 0, because that's where X is, 1, 0, 0. And we update the match edge. We should go from with an A to 3. That's that. Last bit, update the edge here. So we're in state 0, and we read an A. That brings us to state 1. So x has now become 1. Next column, we start by copying, which is copying from column 1. Then we override for the match edge, which is a B, where we should now go to 4. And we update x. We're in state 1. We read a B. That brings us to state 2. All right. Next one, 4. We copy from column x, 3, 0, 0. We update the match edge, which is an A. So here we should go to 5. The rest stays as it is. And we update x. We're in state 2, and what we read is an A. So we go to state 3. All right, and one more time. We copy from state 3, 1, 4, 0. And we have a match edge for C. So here we go to state 6. Let's see if I did it correctly. Yeah, looks all right. So if you want, you can draw the picture from this, right? The same diagram as we had before. I didn't do it here. Well, I did it because didn't do it because I was lazy to prepare it. But I wanted to show the table, because in this case, I think the table shows you much cleaner what happens than the messy arc diagram. And that's basically all. That's how you compute these string matching automata. The code is super simple. Maybe digging through why it does the correct thing is needs a bit of caffeine, maybe a look in the red book. But once you code it up, it's very fast and very simple in terms of what happens computationally. That's the part I want to comment on briefly. Let's analyze how good string matching with the DFA is. I've already said before, when we have the automaton reading through the text once, it is just one table lookup for each text character. That's essentially as fast as you can get. I can hardly imagine speeding that up further. Building the automaton, we still somehow have to fill the table. So even though visually it was copying a column and changing one entry, copying a column is still copying a column and writing every cell. So we need theta of m times sigma time, just because that's the size of the output. The table is that big, m times sigma. So if you add that up, the total time for string matching becomes m times sigma plus m. And also the space for the string matching automaton is the size of the table, essentially, and that's m times sigma. So that's very, very good for the matching time. If you build the pattern automaton once and use it many times, it's probably as good as it gets. But the space overhead can be big. And in particular, sigma in our examples will always be small because my slides are very finite. But remember, Unicode could be your character set. I'll look this up this time. OK, that's from October last year. It was just short of 150,000 characters. As I said before, all the useful emoji and all the scripts that humanity has ever imagined. So it could be big. Sigma could be quite a big number.